Jake Turin's first Lechuguilla trip was in 1989, and he was immediately hooked. He participated in multiple science projects after that, working with Diana Northup and Kim Cunningham, among others. In 2000, he and Mitch Plummer published a comprehensive compilation of Lechuguilla pool chemistry data in the Journal of Cave and Karst Studies. He conducted the isotope work he'll be presenting today while at Los Alamos National Lab. Since retiring from the lab, he's been living and working on an organic farm in rural northern New Mexico. Good morning, Jake, and take it away.
Good morning, Johanna. Can you see my slides and hear my voice?
We can.
That's excellent. So first of all, before we start this, I want to give a big shout out to Hazel and Johanna and all the other organizers. I've been in many symposiums and scientific sessions, and this is running far more smoothly and calmly than many things I've seen. So thank you all for doing such a great job. I really enjoyed the slides yesterday, lots of great pictures. We're not going to have any great pictures in my talk today, but and also hearing the talks this morning, particularly the memories of Kim Cunningham. Kim was the person who got me started in Lechuguilla. Just to give you an idea of how much technology has changed, my very first day trip into Lech was to service one of Kim's data loggers. And the data logger at that point, the memory consisted of paper tape. So results were being printed on a paper tape. As many of you can probably guess, paper tape in that environment did not work very well. So we got about 8 hours of data before the whole thing crapped out. Also spent a lot of time carrying cylinders from hell for the helium study. So it's great to hear the memories of those days. So without further ado, let me figure out how to move this forward. Here we go. So yeah, so I'm going to be talking about data from about 20 years ago. They are complicated, they're difficult to interpret. They've been sitting in boxes in various storage sheds for almost 20 years. They're complicated stuff. It didn't make a very nice package that I could tie up with a bow and publish. Also at that point in time, life interfered and various personal things came along. So this stuff has been sort of sitting off there in the background for a long time. And I really appreciate Paul Berger and Hazel and Max sort of pushing me starting this spring to get off my butt and look at this data and get it out. The good news about that is that there really are some good questions that this data raises, and there's opportunities for people who are younger, stronger, and smarter than me to follow on with this research, and we'll get to that in a little bit. So first of all, why do we care about this stuff? Research into recharge in arid zones is important for a whole bunch of different reasons. Obviously, recharge processes and recharge rates are what determine the sustainable groundwater resources in the arid West and other arid zones around the world. What's the transport velocity? If you've got contamination on the surface or at some particular point, how quickly might it move down through the vadose zone down to the water table? I spent a good part of my career working on the Yucca Mountain project, and this second question of contaminant movement through fractured vadose zones is the key to that. Let me just take a sidebar. It occurs to me that not everyone may know what we mean by the vadose zone. The vadose zone is basically that area of the ground between the water table and the surface. Typically in a sort of standard porous medium, you would consider it unsaturated, but the vadose zone may have local zones of perched saturation. Obviously, if there's a pool in a cave, that is saturated, and if there's drips from a stalactite above, there is a micro-saturated zone above that. So the vadose zone includes those. So what about for cave systems in particular? There is a lot of research going on these last few decades into paleoclimate work based on speleothem isotopics. The general assumption is that the isotopics in a particular layer within a speleothem reflect surface conditions at that point. Well, obviously there is some time involved in going from the surface environment down to that speleothem, where the precipitation takes place. So anything we can do to understand residence times in the vadose zone between the surface and the cave is important for understanding those paleoclimate studies. And with all the work, most of it coming out of Lechuguilla in terms of cave microbiota, understanding what those cave ecosystems are getting from the surface, what the nutrient input is from the surface involves transport through the vadose zone. So these are just a couple of the things that this research could be helpful for. So global fallout radioisotopes. There were above ground nuclear explosions, lots and lots and lots of them starting in 1945. The last one was in 1980. They introduced a lot of radioisotopes into the atmosphere. Lots of short-lived isotopes, which cause the most immediate concerns for close exposure. There are some long-term, long-lived isotopes, the strontium, iodine, and cesium, which are what get the most attention for the downwinder communities. And finally, there's a handful of bomb pulse tracers that are not particular concern from a health perspective, but are very useful in hydrologic studies. You see that list there on the slide. So my study is going to focus on two of those in particular, tritium and chlorine-36. So are these bomb pulse isotopes, are they good tracers? Well, yeah. First of all, we don't have to buy them and put them out into the environment. That's been done for us by the nuclear powers. They are globally distributed. So wherever you might want to do your work, that tracer test started there. The 40 to 50 year time scale is a pretty good time scale for regional or slow geologic processes like vadose zone transport. Because of the range of isotopes, we have a range of chemical properties. A problem, especially in the vadose zone, is that these are very, in terms of chemical species, these are very low concentration. So you need a pretty large sample volume. And especially in the vadose zone, it is difficult to get a large sample volume that's necessary for these analyses. So first one we're going to talk about is tritium, which is an isotope of hydrogen. Hydrogen, the most common form of hydrogen is simply a proton. If you add a neutron to that nucleus, you have deuterium, which is also stable. If you add a second neutron, then you have tritium, which is hydrogen 3. It is radioactive. It's got a 12+ year half-life. The deal with isotopes is that to a first approximation, they behave chemically like the primary isotope. So tritium basically behaves like hydrogen. Hydrogen in the environment is most commonly found in water. So H2O is normal water. If you replace one of those hydrogens with a tritium, you have HTO. So that is in the environment where the vast majority of tritium is found is as HTO. So HTO basically behaves like water. It moves with water. This becomes a little more important is that in any phase. So it evaporates like water, it freezes like water. There are, this is all first approximation. There are minor differences in the volatility, but that's not really important for us. There is natural tritium background due to cosmic rays. Cosmic ray induced neutrons hitting nitrogen in the atmosphere. So you see that spallation reaction there, producing tritium in the atmosphere. Bomb pulse, so thermonuclear explosions produce a lot of tritium relative to the natural background production. The bomb pulse peak was in 1963 in the Northern Hemisphere, 1964 in the Southern Hemisphere. Part of my work at Los Alamos was doing a lot of historical research into nuclear testing, and it's pretty interesting looking at how you can actually tie these peaks into specific very large tests. The big Tsar Bomba that the Soviet Union did, that was the largest atmospheric test, just introduced a ton of, not literally a ton, but a pile of tritium into the atmosphere. The northern hemisphere and the southern hemisphere stratospherically are somewhat disconnected, so we get that offset. By now, it's been long enough since the last atmospheric tests that precipitation now is pretty much back to background where it was before the nuclear age. Because of that 12-year half-life, the 1960s peak has decayed drastically. Tritium is a weak beta emitter. It's not super easy to detect. Basically, it's a beta counting method. For these low levels, there is sometimes an enrichment stage that can be done to reduce your detection levels. Just to give you some idea of how much tritium we're talking about, the standard tritium unit, which we're actually not going to be using that much in this talk, is 1 atom of tritium for 10 to the 18th atoms of hydrogen. So again, we're talking very low concentrations. Radiochlorine. Chlorine 36, the 2 stable isotopes of chlorine are 35 and 37. There's one right between them, 36, that is radioactive, a very long-lived radioactive isotope, 300,000-year half-life. Again, how does it move in the environment? Well, chlorine basically is always encountered in the environment as a chloride anion. So chloride anion, it's stable, it's soluble, it is a very good tracer for liquid phase water. As that water evaporates, the chlorine does not go up into the vapor phase, so it's a liquid phase tracer. There is a natural background production of chlorine 36 in the atmosphere due to cosmic particles hitting argon in the atmosphere. Argon's 1% of the atmosphere, producing chlorine 36 in the atmosphere. There is also epigenic, that is sort of in near surface rock geologic environments where you're getting neutrons from radioactive decay of uranium chain isotopes hitting chlorine or potassium in rock, or calcium 40, also producing chlorine 36 in the subsurface. Well, if you want to make a bunch of chlorine, you produce a whole bunch of neutrons near a whole bunch of chloride. So the big production of radiochlorine from nuclear tests were Pacific barge tests, where you had a huge nuclear neutron flux right near seawater. So 1956, 1958, 2 big Pacific barge tests produced a lot of chlorine 36 and lofted it up into the stratosphere. So once again, it was globally distributed. Since that time, that's all been washed out. We're back to background levels in precipitation. Because of the 300,000-year half-life, that 1950s peak is, though that material is still around and still there. There's no radioactive decay. Measuring chlorine 36 is a little more tricky. AMS is accelerator mass spectrometer. It's spectrometry. It's a very sensitive mass spec technique, and we can measure it that way. Units are again 10 to the 18th, just by coincidence, about the same. So let's see, what was the bomb pulse? Tritium was known at the time to be a big deal, so it was measured at the time, monthly measurements at various locations around the world. You can see the very detailed high-resolution tritium bomb pulse here with a peak in the early 60s. Chlorine 36 was not thought about so much, so this is a much rougher, cruder estimation based on various theoretical reconstructions. So, Lechuguilla Cave, you guys know all about it. Basically, my interest for this study was the fact that those pools give us large volume samples of beta zone water, which is hard to get otherwise. Between 1992 and 2001, I collected over 60 water samples from different pools, analyzed them for tritium and chlorine. all the numbers here have been corrected for decay, so we don't have to worry about tritium decay, and also normalized to the maximum, the local bomb pulse maximum, just so we can compare numbers. So here's a picture of that blue line is Lechuguilla Cave as it was known in about 2000. Those of you who are up on the current stuff know that there's quite a few additions to this map. Those triangles are the tritium sampling locations, various pools in all areas of the cave. Just a little side note, I was really very honored, but because of the subject of my study, I got to visit pools throughout the cave, and I really got a chance to see a lot of the cave as it was known back at that point. Chlorine 36, again, pools throughout the cave. So here, let's look at some results. So this is crude, but we're going to get better. The size of that triangle is a rough indicator of the tritium content. You'll see, and we're going to get into more detail on this, you'll see we have high tritium hits up right in the surface, up at the Liberty Bell area. There's also some large hits down in the southwest, Tower Place, Oasis Pool, those areas. And scattered around, there's a number of other ones. One thing that is interesting and we're going to get to is my laser working here? Let me see if I can make a laser. How cool is that? There we go. Right up here, that's Sugarlands. That's a pool up there in Sugarlands, very close to the entrance and very low tritium value. So we're going to talk about that in a minute. Can I go? Here we go. Huh. No. Okay. Here's chlorine 36. This time, instead of the size of the dots, we're looking at chlorine 36 levels, and you'll see there's high levels in all three branches of the cave, low levels back there up in Sugarlands. Let's look at this in a more useful set of graphs. Instead of looking at the geographic spread of results, let's take a look at depth distribution. So what we're looking at here, this is tritium values with error bars. For all the pools that we've got tritium values on, with depth going down, the y-axis down on the left, and the tritium levels going from left to right. Couple things we see right away is we've got this sort of cloud in here. Up in the shallow, say the top 200 meters of the cave, all of those pools that we sampled up there had measurable tritium above background. You can sort of see down here, there is a dead groundwater level. There's this sort of massive numbers down here at about 0.1%. That is what we believe to be background pre-bomb or post-bomb levels. So there's a bunch of pools down here that have no measurable bomb pulse tritium. Everything above about 200 meters has measurable bomb pulse tritium. When we get lower down, then there's a whole range. There's a lot of variability going on here. The highest tritium we measured in any pool in the cave was up here at Tower Place. This is the highest tritium. It's a good number looking at these error bars, but you'll see it's only about 2.3% of what the bomb pulse maximum was. The lowest, deepest point that we got measurable tritium was down here at about 360 meters deep. Lake of the White Roses, which as I think has been discussed yesterday, and also which we pretty much established in our 2000 paper, that is the regional groundwater, is down here at this sort of non-detect level. I've labeled some of these here just to give you an idea. So let's take a look and see what the chlorine 36 looks like. We're seeing pretty much similar things. The highest level is again in Tower Place. 2.5 meters per year is just, that's how do we get that deep since the pulse? We've got the deepest hit where it's, I would say, is definitely above background is Lake Margaret. That's the same as for the tritium. This is that Sugarlands point. So this is a relatively shallow pool, relatively close to the surface with no detectable bomb pulse tritium or chlorine 36. So what this is, we'll get to conclusions in a few minutes here, but I think the Sugar Lands is interesting, Lake Margaret is interesting, and the fact that everything above 200 meters is clearly affected by nuclear era water. So to get that Lake Margaret number, it adds up to about 9 meters per year. The Tower Place numbers were about 2.5 meters per year. Is that a reasonable velocity for recharge? Well, if we look at local precipitation rates, we assume something on the order of 5 or 10% of that infiltrates, and the other 90 to 95% is either runoff or evaporation. That gives us a net infiltration rate of 20 to 40 millimeters per year. Now, to get from an infiltration, a volumetric infiltration rate to a velocity, we need to estimate what is the volumetric moisture content that's mobile. So picking a number out of thin air, say 1% in a fractured system, that gives us 2 to 4 meter per year downward velocity. So this is all sort of kind of making sense. But what isn't making sense is that these levels are so low. So we're seeing just a couple % of what the fallout peak is. So where did that peak go? Maybe we're just seeing the very leading edge of a diffuse peak. So what was interesting is the idea of looking at how these numbers are changing with time. If we're looking at the bomb pulse moving down through the system, we would see up at the top, if the pulse is passed, that concentrations are decreasing with time, while down below where the peak is just getting there, the concentration should be increasing with time. So let's take a look at that. 2 ways to look at time series. The obvious way is to go back to the same pool over a period of years, and we did that in a couple places. The other thing is to compare what's happening with a drip to what's happening in the pool. The drip is what's just today to the pool is some sort of integrated average of the last few, whatever you have, months, years. So we've managed to do both of those. So here's looking at the tritium time series in the top 150 meters of the cave. And what we see here is, first of all, looking at Liberty Bell, is that the pool, these are hard to see and hard to understand, I understand, but with these error bars, I would argue that the differences between these different years are not necessarily significant. That could just be within the variation of the analysis. But I'd say that the difference between the drip and the pool below it is clearly significant and repetitive over multiple years. So what we're seeing here is that the pool has a significantly higher tritium concentration than the drip, suggesting that the drip used to be higher in the past and that it's as if the pulse has passed. Come down here to Tower Place, where we also could collect pool samples and drip samples. We see the exact opposite. So that's a little confusing. I did warn you at the start that there's some confusing, unclear results here. If we look at the middle depths of the cave, we see time series from multiple different pools. In general, we could argue that a lot of these are going down with time, as if the pulse has already passed, but then some of them are going up. Again, confusing, not sure what to make of all of this. And finally, the very deepest tritium hits, Lake Margaret, Lake Louise, and Nirvana. Some are going up, some are going down. Again, I warned you, this is complicated. I don't have a great answer for you at this point. Chlorine 36, we also see that up at Liberty Bell, the drip is lower than the pool, consistent with the pulse being below. Here, Tower Place, again, this is the reverse that we saw with the tritium, but perhaps those error bars suggest that that's not really a meaningful difference. It's a whole bunch of numbers. These are the numbers that have basically been sitting in my closet for the last 20 years, and making me scratch my head. And Paul has suggested that at least we get these numbers out there and let smarter people than me try to figure out what it means. So we're here at our conclusions. First of all, let's start with the first win, is that this worked. Going into a cave, collecting samples for bomb pulse isotopics, we found a signal. We found interesting signals. We don't understand exactly what they mean, but there is a message here, and this is something that was not necessarily clear from the start that this would be helpful. So that tells us that things are moving on a time frame of decades. Basically, every sampled pool within the top 200 meters of the cave contained measurable isotopes. So that's giving us, if we say 200 meters over those 40 years, something like 5 meters per year of downward velocity, which is a reasonable number. All the way down at Lake Margaret to have gotten measurable isotopics at that depth, that means that some of that water had to be moving as closer to 9 meters per year. And once we get down to 200 meters, there are other pools that do not show any evidence of significant isotopic transport within that time frame. And here's the big duh conclusion, is that these processes are complex, variable. There's a lot of stuff going on. A simple model is not going to explain it. So these numbers we're talking about, meters per year, these are reasonable. These are consistent with recharge rates that we would predict based on first principles. Now, this is a couple points here that I didn't get into in this short talk, but detailed comparison of what's happening with the chlorine and the tritium. Remember, the tritium moves both liquid and vapor phase, while the chlorine just moves in the liquid. We can learn some interesting things about vapor phase processes in a cave from that. The other thing that I didn't get to in this talk is if you look at other caves. So there's also a set of data like this from Carlsbad Cavern and also from Wind Cave. And all of this is in a manuscript that is in production right now. Finally, the time series approach that we touched on at the end is promising, but these results are ambiguous. It'd be really cool to see what's happened 20 years later. And if anyone is interested in, I think I'm a little too old and too feeble to be going back in there these days, but if anyone is interested in collecting those samples, let's talk. As all of these studies are, this is a big team effort. My scientific collaborators, Mitch Plummer at Idaho and Fred Phillips at New Mexico Tech. Paul Berger, really, like I've said, has pushed me to get this stuff out there, and I am grateful to him for that. Paul and John were both very helpful with getting me survey data to put this talk together. Hazel and Max have been very encouraging. Park Service, of course. This was funded by Los Alamos' LDRD program, and it would have all been impossible without lots of cavers who accompanied me on various trips, hauled water samples out. Water samples might be even heavier than cylinders from hell. And when I started putting this list together, I knew that I would probably forget some names. So if you were on one of my trips and I left your name off, my apologies, it was unintentional. Let me know and I'll make sure it gets in there for the next talk. So thank you very much. I really appreciate this opportunity. I really appreciate the organizers for putting this symposium together. Thank you.